Yeah, okay. So space weather is generally referred to as the study of Sun-Earth connection. So by now, I assume that you might be knowing that Sun has a dynamic magnetic field. It goes from solar maxima to minima, where the magnetic field activity is more in maxima phase, lower in minima phase, and again it goes to maxima. So the magnetic field of Sun is very dynamic thing. It keeps on changing, and that changes in the Sun's magnetic field has a direct impact on the Earth's magnetic field, by which in turn affects the also it also had the effect on the ground. So these kind of effects are mainly due to the magnetic field, but not only due to the magnetic field, and they produce some geomagnetic induced currents, because you know that if we change the magnetic field, the change of magnetic field produces electric current. So the same thing is there, and there is a high voltage in a very slow time period, so short circuits will happen. So from there, uh, we have direct implications which could be very hazardous, including the disruption of communications, electric power, also the GPS network, and the aviation. If you are flying over the polar regions, there may be highly energetic particles present there, so it could be hazardous to health for the flight members. And again, as the GPS is like affected, the aviation obviously gets affected, and the satellite functionality is also affected if some energetic event is passing through, and there is a okay. Let me go back. So passing through, so satellite may also get if impacted. And obviously, if you are in the space, so it is going to directly affect our health. So the question arises that can we really prevent these space weather events? So unfortunately, you all already know the answer. Yeah. So even then, is there anyone who thinks that we can prevent these kind of events from happening? Okay. So they are bound to happen, just as the tsunami, earthquake, tornado, flood, these things are going to happen. We cannot control it. What we can do is actually mitigate its effect. Just like when tsunami is happening, we have a forecasting system that at this time tsunami will be happening, so we can like take some measures to mitigate its effect. So the loss can be minimized. So that can be done through the space weather forecasting. And this is done through the continuous observations using remote sensing as well as in situ data. So these are some of the major remote sensing spacecrafts in the space. And obviously this is Sun. I think everybody knows this one. This is Earth, and this is a spacecraft, just a logo of spacecraft. And this is I've tried to draw a CME-like structure, uh, which looks like pizza slice, but yeah, just treat it as a CME thing. So this whole observation thing or the continuous observation provides us about the information that when this is going to happen. Okay. So this whole study of space weather can be classified into three domains, starting with the solar domain, in which we talk about mainly solar surface to solar corona. And there is a heliospheric domain, which starts beyond the upper coronal region, and then again the Earth's environment, where we have the magnetopause, magnetosphere, ionosphere, and these kind of things. So in this whole talk, I will be mainly focusing on the heliospheric domain, and the reason is very clear because what we are trying to do is to understand the underlying physics, that how these things are happening, and then further we can prepare our rational response to mitigate its effect. But the problem is that in the heliospheric region, these space weather drivers like CME or solar wind, they become so less dense that it becomes very challenging to observe from remote sensing. So from remote sensing, you can get the full picture that these things are moving and how what's their structure. So these kind of things can be totally derived from the remote sensing. But since they are so dense, we cannot see it properly. Hence, we cannot make any deduction from those data. And in this case of in situ measurements, so if you see, if I allow this CME to pass through it, so if you observe, the CME has, or this piezo slice has three marks or three holes in it. But in the in situ one, that spacecraft actually just observed only one. Okay. So they provide very critical information, but very locally constrained data is there. So we cannot draw a complete picture of what is happening in that region. So in these kind of situations, especially in heliospheric domain, these numerical simulations become very handy. So what we do in numerical simulations is that we use the existing physics, and then we postulate, or we try to like quantify that this is the best theory which will be acting here. For example, like MHD or machine learning or some empirical relations. So we use the observational data. From there, we know the existing part, and then we apply our theory, whether it's MHD, AI, ML, anything. And then we try to verify it using some in situ data. Because once you have made the model, you must verify with the observations. And once you have all these things, so now you have successfully made the model. So the question from the scientific part, from the viewpoint of heliospheric work, is to develop a global solar surface to coronal field model. From the sun's surface, I don't know why it's going. Okay, so from the sun's surface to the in the full corona. So there we have to kind of model the magnetic field lines, because they are the main culprit of these whole things. And again, we also need to have a solar wind model, because they are the continuous outflow from the sun. They are omnipresent, they are everywhere at every time. And obviously CMEs, the coronal mass ejections, are the most energetic phenomena of these space weather events. So it's also important that we have a forecasting model of the CMEs also. So before diving deep into the numerical algorithms and the models, let's briefly define the space weather drivers so that we are on the same page. The solar wind is basically defined as the continuous outflow from the sun, mainly to the pressure difference, if we just talk about the macro scale. And you can see in this one, I hope it is visible, that these little things are going, dust-like structures are going away from the sun. That is basically solar wind. And if we talk about the CME, coronal mass ejection, then you can see at this point, this gigantic structure, it's a very big magnetic cloud. So if you want to imagine its size, then you can say that the pointer is even bigger than the Earth, okay, at this scale. So you can imagine how big is the CM. So this is a coronagraph image. I hope some of you are familiar with this one. So what we do is that we occult the sun so that the intensity in these regions are very clear, so that we can see the whole dynamics of the CME. So from these coronagraph images, we can estimate the velocity or the speed of the CME, as well as their structure, their angular width, angular height, and these kind of things. Okay, and obviously their direction, that in which direction they are propagating. There's also one more thing, solar flare, which is a highly energetic event, mainly containing the electromagnetic outburst. So they don't have much plasma inside them, but they can accelerate other particles, which are called solar energetic particles. But we'll not be focusing much on the solar flare. But the only thing I would say about the solar flare, that as it's an electromagnetic disturbance, it can like produce radio out, this radio burst also. So it can be a radio blackout situation. So we know that all the cell phones and all these things are based on the radio waves. So if there is a radio blackout, so there might be a problem. So it's not that the only CME and solar wind are the main thing to study. Solar flares are important too. So coming to the numerical approach. So if we just classify on a broadly, then we can say that any numerical model can be classified into these three categories. Starting with the empirical models. So empirical models are pattern-based or probabilistic-based models. You can imagine it as a machine learning or AI-based models, where you know that this is the thing that we are observing, and this is the effect. And from there, you try to find a pattern, and from there, you have a model. So the better the pattern matching skills and probabilistic method, the better will be or accurate will be the model. The next is the semi-empirical models. So which kind of lies between these two. That's why it's semi-empirical. The semi-empirical models actually employ a empirical relation. So by empirical relation, I mean that it's again kind of pattern recognition, but not totally. We have a equation based on long-term study. Okay, just like say Pythagoras theorem. Okay, we cannot prove it. I hope somebody can, but it's based on long-term. It's kind of empirical relation, but which works. So in the similar manner, though it's not very simple to have a very good, a strong empirical relation, but if it is working, then we can use it obviously. The reason being that why we use this semi-empirical or empirical, because they are very fast. They are computationally cheap and you will get the result instantaneously, maybe in case of empirical models. So that's why these becomes handy. So depending on the scenario, on the situation and the time that you have to solve the situation or the system, and plus the computational power that you have, will decide which will be the most suitable one for you. And finally, the MHD models or the analytical models, they are physics-based models that which uses the observations, and from there you solve on the basis of the physics. Let's say that I assume, let's say that we made the approximation that in this heliosphere MHD is working. Then we'll use the observations of the solar surface, and from there we'll use the MHD equation to solve everything. Okay, so there are multiple models right now, and let me clarify that they are not finalized version of these models. They are still developing. They're in the development phase. So I've just mentioned few. These are some machine learning based models or empirical models. These are some semi-empirical models. We also have some Indian models. So I've just used the earlier ones. Okay, so we have also some Indian models. And the MHD models are also there in the MHD model, because we have all the physics containing in it. So we can also forecast as well as we can do physics also, just like through the observations. So these models become very popular because the physics they can do. So INLIL is the most widely used model. You might have heard, if you have ever heard of any MHD models. It is US based, same with space weather modeling framework. So you can see it was the INLIL was developed in 2003, which is a very long time, right? So they are still refining it. Okay. So it's kind of, they reached a threshold point from beyond which it was taking much time to improve. In the meantime, rest of the world, like Japan, Europe, has also made their this MHD model. The Japan one called Susano, with obvious reasons, and the Europe called their model as the Euphoria. And in the last year, we have developed and we called it Swasti because it's Indian, so we named it Swasti. Okay, so just briefly, let me introduce the Swasti. Swasti stands for Space with Adaptive Simulation Framework, or Swasti framework, and it has twofold purpose. One is obviously forecasting, and other is the study. So what we are focusing on, so what's the objective in forecasting? We are mainly focusing on the solar wind plasma properties in the inner heliosphere, and also the stream interaction region, of which I will talk about in the next slides, and obviously the CME, or the coronal mass ejection, their properties, their evolution, and obviously the arrival time at the Earth's location. And we can also study these things because it's physics-based model. So we can generate some certain scenarios and see how they are behaving in those kind of situations. So it's kind of simulating the reality. So again, we can study the high-speed streams or the different varieties in the solar wind and the stream interaction region, and as well as the coronal mass ejection. So let's start with the solar wind now. Okay. So how many of you know what is a magnetogram? Anyone? Okay. Some of you know what is magnetogram. Then let me. So I will define magnetogram. So bear with me that there is something called magnetogram, which gives the magnetic field of the solar surface. Okay. So it is based on observation that we are continuously looking at the solar surface, and from there we are getting the magnetic field of the solar surface. Once we have the magnetic field, that will be used as the observation-based input to the model. And then we compute everything, and finally we get the plasma properties in the inner heliosphere. So strictly speaking, by inner heliosphere, I mean anything beyond 20 solar radius and before Jupiter. Okay. So it has two domains, coronal model and the heliospheric model. So why two domains? The reason being that the dynamics or the properties in these two domains are quite different. So we need two different models, okay? From solar surface to approximately 21 solar radius, things are a little different as compared to beyond 20 solar radius. So just quickly, let me go through it, and then we'll again go through in detail in the next few slides. So there is something called PFSS model, or the potential field source surface model, which extrapolates the magnetic field lines from the solar surface that we got from the magnetogram to something called the source surface. Okay, So I will define these kind of terms, just giving a brief overview. And again, there is something called scattering current sheet model. So these kind of models was already given in 1970s, 80s, based on the theories, on the plasma theory. So from there, you can make your own numerical model based on those theoretical models. So this PFSS model extrapolates the magnetic field lines, and there is something called again WSA model. So WSA model, as you saw in the few earlier slides, it's a semi-empirical model, which means it will use some observational data, and it will have an empirical relation, and from there it will give something. So it provides the speed at this boundary of this coronal domain and the heliospheric domain, which I have taken as 0.1 AU. And from there, we have the speed, and based on some other assumptions like the conservation of kinetic energy, as well as this Parker spiral structure assumption, you can have the density profile based on velocity, magnetic field profile based on velocity. And if you assume thermal pressure balance situation at this point, which is kind of okay or good enough approximation, then you have all those 8 properties which are needed to do this MHD simulation. So you might, some of you might be knowing what is plasma and what is MHD, but if you don't know, then maybe in next couple of days there are lectures on it. So I will just briefly talk about MHD, not much. So MHD has basically same kind of HD thing, hydrodynamic, but with magnetic field. Okay, that's the only difference. But the magnetic field is a very notorious thing because change in magnetic field creates electric field. So and vice versa. So it becomes very difficult to deal with. So the MHD becomes computationally much more expensive as compared to HD. And another thing will be the Maxwell equations and these things. So from MHD, we'll need velocity vector, magnetic field vector, pressure, and this density. So if we have all these things, then we can start the MHD equation because we know the initial condition. From there, we can start. And if we do all these things, we do these things using Pluto code. So Pluto code solves the MHD equation for us. It's an open source software kind of thing. And from there, you have the plasma properties. So what you have to do is to make this blue line inside whatever is the blue line as realistic as possible. Okay. So it depends on you that how you define these parameters and make it more realistic, because the more realistic the model, it will be more accurate and it will be more it will be more in a better manner. It will complement the observations. Okay, so this is the magnetogram. Okay, so you see this is the sun, and these white and blue patches are there, which are basically high magnetic field regions with opposite polarity. And you can see this is the sun, and if we take this kind of projection of it on a 2D plane, this is called the synoptic map of one Carrington rotation. If we take this from, if we take the full rotation and then flatten it in a 2D map, then this is called Carrington rotation, in short CR. And this time period varies actually, and it is approximately of 27 days. And there are multiple magnetograms available right now. Gong is a ground-based magnetogram, and India is also a part of it in Udaipur. HMI, which is on board SDO, it's a space-based magnetogram. So if you have a space-based, you can see the resolution is much higher as compared to ground-based, but both are quite good and giving very good scientific results. So now let's quickly see some results. What will happen if we extrapolate? Okay. So we had the magnetogram. This was the magnetogram, and then we did the extrapolation of the magnetic field lines. So this is this dark green. Is it visible? The dark green color. This is the coronal hole. Okay, up and down. This is the coronal hole, and these are some active regions at near the equatorial line. And this cyan and orange are the open field lines of opposite polarity, and these gray shades are the closed field lines. So our interest is only on the open field lines, because only those field lines will reach the location of Earth. Okay, so our main focus is there. So what we are trying to do in this one is that we're trying to do one thing, that from where these field lines are originating, and that is marked by the red colors. You can see, like for example, if you see that these field lines are originating from this location, right? and these field lines are originating from this location. So it's not like that whatever the field lines are arriving at Earth are coming from the coronal hole regions. Rather, it can also arrive from the active regions if they are big enough. Okay. So why the foot point is important? For example, if you see one field line is coming from here, obviously it will depend on the resolution you take, but you can see some of the field lines are coming from very distant places. So this will become clear that why this is important. So if we make a map, okay, that let's say that it was only about the earthbound field lines, because you can see it is reaching the Earth's location. So it's like the field lines are coming in the front direction, but I'm taking a projection, so it is looking like this one. Okay, so only those field lines are there which are reaching the Earth's location. Now let's say that also focus on other field lines, all the open field lines, not only the Earth directed field lines, and we mark and we compute this D parameter. D is basically how deep inside this green area this red dot is lying. Okay, so what is the degree of this red dot to its nearest boundary of the green region? Okay, so if you plot this, compute the D value and plot it, this is what it will look like. Okay, so all the field lines that are arriving in the equatorial plane, so this minus 60 to 60 is basically the latitude of the heliosphere. Okay, so if you take the whole heliosphere, so the theta will be going from minus 90 to 90. I'm just showing from kind of minus 75 to 75. So you can see in the this region, equatorial region, this D degree is lower, but as you move up or low, this D value is increasing. So this is the color map. You can see blue is for the lower value. Similarly, there is something called expansion factor. Okay, so imagine the magnetic field lines as a tube. Okay, simply tube. Maybe a cylinder type which you use to study in the fluid mechanics. And as if you go radially advance, then this tube is expanding. Okay, so that is if you assume the magnetic field lines to be a tube-like structure. So if you go away from the sun, it will be expanding. So that is called the expansion factor. Okay, so it also depends that how much the field lines or the field line tube or the magnetic field tube is expanding. So these are two things which are taken account in the WSA relation. That's what I am showing. So one is on the basis of that, how deep inside the coronal region the open field lines are coming and how much the magnetic tube has expanded. So these are two things. And this is the logarithmic scale. That's why you are seeing this. And this is basically the heliospheric current sheet region. This is just a fancy word. It only means that the magnetic field lines are changing their polarity around this point. Or polarity inversion line, you can also say. Okay. So this is the WSA relation. Okay. So as I said, it's a semi-empirical relation, semi-empirical model, or you can say, where you have an empirical relation based on some critical observations. So we had D degree, which is the nearest theta degree from the periphery of this coronal region or coronal hole or active region, and we have the expansion factor. Now, if we have both, you can see D is here and expansion factor is here. So now can you say that whether the expansion factor is directly proportional to speed or indirectly proportional to speed? Okay, raise your hand if you say directly proportional. So V is the speed of the solar wind from WSA. So is it directly or indirectly? So it's in the denominator. So obviously it's indirectly proportional to it. Okay. So it was an easy question. Come on. So it is indirectly proportional. And again, you can see D is on the upper value. So it's directly proportional. So it means that if the field line is originating from deep inside the coronal hole region, so it will be having faster streams. And if it is coming from very like periphery of these regions, so it will have a slower speed. But that's not the only thing. The expansion factor is also important. And plus, there are some independent parameters also, V minimum, V maximum, W, and beta. So actually, you can say 3, because we found that if we take the median of D as the value of W, it works very nicely. So we can get independent of this one parameter. And again, we have these 3. So there are multiple studies, long-term studies, where they have found a suitable values of these independent parameters, such that in the general scenario, we get a very good result. Okay. But these values will differ if we have a different state of the sun. Like in the solar maxima, these values may not be the perfect values. And in the solar minima, there might not be the best suitable values. So just this is an empirical relation based on two different critical observations, expansion factor and D. And from there, you have this speed plot. Okay. So we made the plot of D, we made the plot of Fs. And if we use just the empirical relation, we have the speed. So now we have the speed of the solar wind based on a semi-empirical approach at the boundary of these two domains, coronal inner heliosphere domain, which lies around 21 solar radius. Okay. So from here we have the speed plot, and based on this we have the magnetic field plot. Okay. And there are multiple reasons why we are not just using the extrapolated magnetic field line and taking the value based on this speed, because there is something called open flux problem. So from a long-term study, we saw that whatever we are estimating from numerical simulations is rather lower than what should be there. Okay. So there is something called open flux problem, which is not solved completely till now. So it is better to take preventive measures. So a speed-dependent magnetic field gives a better value. So let's dive deeper into this one, that what is happening physics-wise. Okay. So this is sun, 1 solar radius, and then we have something called source surface at 2.5 solar radius. So source surface means assume a surface beyond which or from which the magnetic field lines have become almost radial. Okay, that's called source surface. The reason will get clear. And in this region, this plasma beta, you know plasma beta? Yeah. Okay, great. It's the ratio of gas pressure by magnetic pressure. So if the plasma beta is low, then what does it mean? That the region is magnetic field dominated, or the force dynamics will be governed by the magnetic field. Okay. So it means that magnetic field is dominating this region, and beyond this point, something else is happening. Okay. That's why there is some region forming. And this source surface, which also means zero potential surface. So if you know the magnetic field at this point, okay, at the solar surface, and if you assume that something like this happens and the potential is zero, then it actually you have two boundary conditions, and both are potential actually, because we are only taking the BR component here, and here the zero potential surface is there. And from there, you can say that there is something called uniqueness theorem. And from there, you can say that there will be a unique solution between these two boundary conditions. Okay. So this is the reason that why we are assuming this kind of thing. And this is not a crude approximation. This is kind of valid, because beyond this region, the plasma beta becomes greater than 1. So when I say in this region, beyond this region, it's not a strictly thing. It's not like definite, because after 2.5 things will become like this, like that. No, it's kind of approximate symmetry that we are taking. Plasma beta can become greater than 1, maybe at 2.1 or something like that place. But just to have a symmetric system to make our life easier, we are taking in that manner. And obviously the field lines are just originating. There is no highly J value. Current sheet region is forming in this region. So assumption of J is equal to 0 is kind of a good estimation. And the source surface can be taken at 2.4, 2.6 or anywhere. Okay. But it depends on you where you are taking and at which value you are getting the best results. So what I found that I am getting a good result at 2.5, and most of the other models are also taking 2.5. But in some situations, 2.3 may give good results, or 2.7 may give good results. So it's based on that whether you want your model to be more generic or more concentrated towards some specific events, or in the solar maxima or solar minima region. Okay. So those things will decide the exact values of this. So if you are not able to visualize, then this is what I'm talking about. There is no sun here, just the magnetic field lines. The black ones are the closed ones, and obviously blue is going away and the red is coming inside. So this is what I mean by extrapolation of magnetic field lines based on the magnetogram. Okay, so this is SCS, a scattered current sheet region. The only difference between the potential field source surface and this scattered current sheet is that now we assume that in the polarity inversion line, there is a current, non-zero current region there. Okay, so we have to incorporate it. Means the magnetic field lines will bend and kind of form hook-like structure. So it will not meet, rather it will get closer and closer. And that is what the current sheets are called. And so there is non-zero current region in this. So if you just take PFSs, that won't be a good approximation. So we are taking a scattered current sheet. So there now we have a high plasma beta, and beyond this, if everywhere the plasma beta was low, so you can see that there will be a point after which the pressure gradient will be like the more powerful thing, and hence a radial flow is kind of good estimate. So now the pressure gradient is dominating the dynamics in general scenario. Okay. So this source surface was at 2.5, and beyond 2.5, if you go till 21.5 solar radius, that is the boundary of this SCH current, scattered current sheet region. So we have extrapolated the field lines from solar surface using magnetogram till the 21.5 solar radius. Okay, and this is the coronal domain, beyond which lies the inner heliospheric domain. So you can take 21.5 to be 20, 19, 18, 15, anything. But it's based on one thing, that there is something called Alphen radius. So before this, the solar winds, in simple words, if I say, anything or the solar wind which is coming out can go back. Okay, but after this region, it will not go back. It will just radially expand. So there is a region. It will not be a spherical structure. Rather, it may be of oblate or prolate structure, but either of them, not both. But it not be necessarily spherical. But again, to make our life easier, we are taking in that manner. And whatever assumptions or approximations you are taking, it's okay if you are getting the good results. If you are not taking good results, even a valid approximation doesn't make sense. Okay. So everything finally should give a good result so that it's worth enough to do it. So what will happen beyond this point, coronal domain? So as I already told, that the coronal domain is based on semi-empirical approach, and beyond this one is the MHD. So now we use MHD code to solve the MHD equations, and we use ideal MHD using Pluto code. We have the speed profile from the WSA. Assuming the kinetic energy to be constant, you can say N is the, not rho, and N is the number density, rho is mass density. Okay. So from there we have the number density, and BR, which is the radial component of magnetic field, is based on the velocity. Okay, you can see. But we have extrapolated field lines, so we know that if we talk about this point, so from where this field line have originated. Okay. So this is important because from the solar surface, the field line is coming, and that is basically guiding those particles or the solar wind or everything. So you need to have a control that from where the magnetic field lines are originating. If you don't know that, then how will you conclude? Okay. So this is very important. We need to extrapolate these field lines, and from there, the MHD will take care of those things. But if you want to draw it, then you will have to do it yourself. So once the extrapolation is done, we have the speed profile, and based on these things, which is density, magnetic field, these two things, and obviously if we take the thermal pressure balance, then we can take a constant pressure at this radial distance. This is not totally accurate thing. The pressure is not constant. Okay, but let's see what happens if we take the pressure constant. It's rather better to take pressure constant as compared to density. But overall, there is not much difference at one solar radius, let's say 21.5. It might go from 5 to 7, kind of these. So the computational domain, of which I will talking about in the next slides, is going from 0.1 to 2.1. Okay. So there is nothing holy here. You can take any values. Obviously, the initial value is 0.1 on the base of extrapolation. You can go to 3, you can go to 4, you can go to 1.5 anywhere. The theta is going from -60 to 60, because we know that the Earth lies from -7 to 7 or in the equatorial plane. So that's why it doesn't make sense to solve up to higher latitudes. Let's save some computational power. So phi goes from 0 to 360. You have to take it because phi is important. So the Earth is rotating, and the Earth is obviously taking the whole phi. Yeah. SDN. FGN and VR. Okay, in this slide. Okay. Okay, so SGN, by SGN I just mean the sign. Okay. So by sign I mean that if you see these arrows, the blue arrow and the red arrow, it's positive polarity, negative polarity. So at this point, the magnetic field has to be plus. So I'm taking the magnitude of that based on speed relation, but the direction is the same. Okay, that's why there is a sign of B corona means the extrapolated one. Okay, using that one. And B phi is a longitudinal component. Okay. Okay, so if we solve everything, if we do everything rightly, then this is the movie that we should be getting. So this is again in the resolution of 150, 120, 360. So whenever anything like this is written, it means r theta phi. If we are in the cylindrical coordinate, okay. Sorry, spherical coordinates. So everything is on the in the spherical coordinates because by now you have seen that there is a spherical symmetry. So it makes sense to have to be in the spherical coordinate system. So in r it's 150, theta it's 120. So you can see in theta and phi there is 1 degree resolution, and in r it's approximately of 1 to 2 solar radius. Okay. So I don't know why this movie is not playing. Yeah. So this is the R phi plane. So I hope you got what I mean in by R phi plane. Right. So the equatorial plane, if you imagine the equatorial plane in which the Earth revolves around the sun, that is more like the R phi plane. This is R theta. You can see the location of Earth, Mars, and Venus also. So it is, if this is the sun, this is the Earth. So this direction is the theta direction. Okay. And this is phi. And this is basically theta phi plane at r is equal to 1. Okay. So I don't know why movie stops, but anyway, so you might have seen the spiral structure. So spiral structure is forming, plus you might have observed that the blue is for the high speed streams. So high speed streams are more localized at the higher latitudes, and the speed at the lower latitude around the equatorial plane is lower. And this zigzag thing, which is at the initial state of simulation, it will become more smooth. This is basically corresponding to the current sheet region. Okay. So magnetic field is not there. Okay. But in magnetic field also, you will see the same kind of structure. And this is density. E is the, okay, E is density. It's not with C, rather E. And this is the temperature. So the density and temperature are in logarithmic scale because the difference are very minute. So you have to take in the logarithmic scale to find the patterns in those things. So you can see the current sheet region is being seen in all these things. There will be in magnetic field also because that is the where polarity changes. And here at this point, the density will be higher and the temperature will be lower. So these are some of the properties that you can directly draw from just this plot. Okay. So that was some fancy movies. So let's talk about validating with observations. So what we do is that once we have the whole simulation, yeah. Okay. Let me go back again. This one. So this is the current sheet region. But we will say current sheet from this part rather. This is the low speed region corresponding to current sheets. And this is the, yeah, now it's good. So this is the, you can see, this is the kind of structure of the current sheet region. And here the density is higher and the temperature is lower. And the magnetic field lines are changing their polarity. Okay. Okay, how will you visualize its structure? Okay. So if the movie plays again, otherwise I have to show my hand. Okay, I can use the board. Okay. So let's say if this is the sun, so something this sort of will happen if this is the whole heliosphere. Okay. So imagine this 2D plot as 3D. This is the sun. This is backward. This is frontward. So this is the region of the current sheet. And this is where the magnetic field lines are kind of this is going. So it's very difficult to draw Rather, it's just imagine that something circular. I just have you rotated something like this? If I just put it inside this one and rotate, so if it's a very like cloth-like structure, so it will more like the skirt will this rotate. So it's kind of there will be some theta variations. So that is also reflected in the current sheet region. It's basically that just put a cloth inside a rod and rotate the rod. The structure that you will get will be the current sheet region. It's like that. Okay, so let's come to the validation with the observations. Okay, so there are 5 Carrington rotations. By now, you know what is Carrington rotation. So one complete rotation or time period of the sun, and this is 205377. So these are basically some of them are in the solar minima region, and some are there in between the solar maxima and solar minima. None of them are from the solar maxima. Okay, because in solar maxima it's very dynamic. There are continuous eruption of CME. So if you just want to compare the ambient solar wind, it is suitable to take those current rotations in which there was no halo CME or no CME pass through that particular spacecraft. So I'm comparing with the wind data or the Omni data, which is at the Sun Earth L1 point, okay, just near to the Earth in the Sun direction. So you can see that blue one is the MHD solution, and what are the things that can be concluded from these plots is that the main features like the rise here, the rise here, and the rise here are being captured nicely. And some very fine things like the slope here is not matching very nicely. And the same pattern goes everywhere. Okay. The main structures are being captured. There may be some time lag because you can see the peak of observation, which is in gray, and the blue is little different. So there the structures are matching well, but there is a time lag, and plus some minute differences are also not getting captured. Okay. So these are some things. So we can say that over a large, on the large scale, if we take this is of 27 days, if I take it of 100 days, it will give a good, better match, or at least through in the eyes, it will look a good, better match, because the large scale structures are matching better as compared to small scale structures. And this red line is the HUX. So HUX stands for heliospheric upwind extrapolation technique. So it just takes the WSA speed relation and extrapolates it, assuming there is no magnetic field, no gravity, these kind of, just on the basis of that you just expand, assuming that the gradient of pressure is constant. Okay. So from there, so in simple words, it's an extrapolation technique, not an MHD thing. And the MHD is for blue and the HUX is for red. So there are some differences in HUX and MHD, not much rather in case of speed. You can see that in some regions like this region, in this region, the rise in HUX is very sharp, like in this region. Okay, I have some shaded region. So in these regions, you can say there is a clear difference between the HUX and MHD. So MHD is kind of taking gradual rise here, whereas the HUX is rising very sharply. That is mainly due to the things that are not taken account into the HUX, like the more realistic pressure and the magnetic field, these things. So that's why this rise is gradual as compared to the sharp rise. And if we talk about the other plasma properties like magnetic field, density, temperature, so these things cannot be provided by HUX because HUX just extrapolates. Okay, so we only have speed from WSA, not density, pressure, and these things. So you can see the speed. What we did is that we did took different values, that assuming that the system is behaving slightly different manner. Let's say that if it's the MHD system and you are taking different values of polytropic index or the ratio of specific heat, Cp by Cv. Okay. If you are taking different values, then it will solve differently. Like 1.67 is for the adiabatic. If I assume the whole thing to be adiabatic, then we'll get these blue lines. And if we take it to be 1.5 or 1.3, then we'll get correspondingly different things. So just by visualizing these things, you can conclude that the green one, which is corresponding to 1.5, is giving the best result. But the main thing is that we have these things, and the main structure features are matching. Not very with not very good magnitude match for temperature and density, but the features are still kind of matching. Means for rise, we have a rise in the observation, in the simulation also. And one more thing is that the density is getting overestimated. If you talk about anything, gamma is equal to 1.67, 1.5, and the temperature is getting underestimated. So we have to take some measures to take into account. So this was all about the solar wind, or the modeling of the solar wind and the validation. Let's talk about some of the perspective of the Aditya-L1 through which we can complement using this model. So now it must be very clear. This is the sun. This is the ecliptic plane. And you can imagine the heliospheric current sheet to be like this, but of some distorted shape. Okay, not very clearly like this one. And the spacecraft or the Earth location is not at 0 degree latitude, rather it will be moving from plus to -7. So let's imagine it to be here. And from there, you can say that if we take the computational surface, or just imagine a surface in front of it, on the right of the bottom of it, and then we can measure the properties at these points, because we have the solution of solution at every place from 0.1 AU to 2.1 AU. That's the main benefit of doing numerical simulations, that we have the data at each and every point at every time. So if we take form computational surfaces in encompassing that spacecraft, assuming it to be Aditya-L1, and if we take the average, then there were some interesting conclusion that we were able to make. So just to briefly introduce Aditya-L1, I hope you already know it's the first Indian space mission to study sun, and it will be at the halo orbit. It will not be at just one point, rather revolving around the L1. And okay, leave this point. It has 7 payloads, 4 remote sensing, and 3 in situ instruments. And we'll be mainly talking about the in situ instruments, obviously some chronograph, which is basically remote sensing. I hope you know what is remote sensing and what is in situ. Okay. So whatever we see from our eyes is kind of remote sensing, and whatever we feel from touch is basically the in situ kind. So SPEX is one of the payloads, in situ one, which is designed or with the objective to study the solar wind or the energetic particles. And let's see what we can do here. So let me define the stream interaction region first. So let's see that this is slow stream, slow solar wind, and this is fast solar wind. Okay. So the fast will rotate less as compared to slow. Omega is constant, let's say. Okay. So then there will be a compression region, and this compressed region is called the stream interaction region. Okay. So it's just basically a compressed region between slow and fast stream. So this compressed region is very interesting. It has some peculiar properties, and 75% of the space weather activities in solar minima are due to these SIRs, or stream interaction regions. That's why it's also very important. So the thing that you are saying is basically from 1971, so it's very, very old. And in that particular paper, they have also talked about few things we have generated from our simulation, but has not been explored very much. So typically, to define SIR, we use speed, magnetic field, and density properties. Okay. So if you see, it's a very weak SIR, around 300 and going up till 500 around. So it's a 200 kilometer per second gap. So it's not very high and it's not very, very low. It's kind of moderate. And in this region, which is this shaded region, you can see the magnetic field line are rising. The density is also rising. And there is some fluctuation in the velocity phi component. And leave this flow angle. So you can see there is some characteristic property of SIR. The magnetic field will rise, density will rise, just because the density has rised in this, the compressed. So magnetic field, if we compress the magnetic field lines closer, the magnetic field and density will rise, and hence the magnitude will rise. And similarly, if the particle has concentrated in this one, the density will rise. Okay. So it's very intuitive, these two things. And obviously, this velocity difference should be there. So it is coming. So mainly these things are used to define this SIR. So what we did is that earlier we draw this thing, assuming it to be SPEX, and we know SPEX has one unique property or unique feature, that it can measure, it has multi-directional observation capability. Okay. So it will observe the particles in the sun's direction, different directions, upward, downward. So there are multiple windows in aspects. So what we found after the simulation and taking the average, that if we look at the proton flux, this rho v theta, in the theta direction, so there will be a dip in this one, okay, and there will be a fluctuation in v5. So this is not a very new thing. It was in the theory, but we produced from simulation, and very recently it has also done through observation also. Okay, but people are not focusing much on this one, which can also possibly be concluded as one of the peculiar properties of SIR, which can lead to more robust algorithm to detect the SIRs. Most of the spacecraft right now at L1 don't have multi-directional observation capability as aspects. So aspects can kind of complement these observation or simulation results. So that's all about the solar wind. Now let's quickly come to the coronal mass ejection, which is CME. So one of the fascinating things. So for CME, first of all, we need to have the ambient solar wind. Okay. Background नहीं है तो फिर अच्छे से नहीं होगा. So we need the solar winds, and we already talked about the solar. Now we have to start with the CME based on the observation, obviously. What are the properties of the CME, how the CME looks like, and how fast is the CME? We don't know. Okay. So we need some observation based properties of the CME initially, and then we will simulate it. So that is based on the coronagraph white light images. Okay. Stereo, LASCO, or different things. So I hope some of you have already used coronagraph white light images, and I also showed a video earlier. Are you guys comfortable with the coronagraph images? You know what is coronagraph images? Everyone? Okay. I think not everyone. But it's just like seeing the sun just by occulting it. So we are just assume that I'm seeing this light by using my hand. So we are not able to see the light. So the fainter things just and the periphery of those light will be more visible. So that's the same technique that we use in the coronagraph white light images. And from there, we have some sense of where is the CME, how fast it is moving in those different images. And from there, we can use fitting techniques. And from there, we can deduce about their structure, their structural properties, and their kinematic properties. And with some confidence, we can also deduce about their thermodynamic properties or density. But we need 3D things because we are doing 3D simulations. So it becomes very difficult to have a very good estimate of the 3D things of like magnetic field orientation of the magnetic field, or the density profile of that, or the temperature profile. So in case of CME, not everything is being provided by the initial observations. So you need to have some parameter estimation or use some standard values related to that CME. So the CMEs, the density in the CME don't vary like very much, the 10 of the order, like it will be around 10 to the power minus 18 kg per meter cube, but it will not go to -9. Okay. It might go from -20 to -18 or -17, but that's the only range. Okay. So you have to take some standard values based on iteration. You know that this is working, and plus this has been observed, this has been reported. On the basis of that one, then we'll use our model, and then we have the CME properties in the inner area as well. So in this one, even in the earlier one, we talk about the forecasting and also what physics can be done, like the SIR case. Similarly, in this one, we'll also talk about. So currently we have two models, the cone model and the flux rope model. So cone model is a simple one, having a simple geometry, homogeneous density, homogeneous temperature, and linear speed. So the whole structure has the same speed. So it's a basic model, very fundamental one. And the next one is the flux rope model. So I will just leave this cone model and go to flux rope model. Okay. So the flux rope model, you can see this. It's a magnetic cloud. Okay. So you can see these lines, colorful lines. Those are basically representing the magnetic field lines. It has all the three components. Just on the contrary, that the cone model does not have a magnetic cloud. It's just HD cloud. Okay, there is no magnetic field lines. And it can have a complex geometry. So it has a capability to incorporate those complex geometry. Let's say from the coronagraph images, we saw some distortion in the CME structure, not just like this flux rope structure, rather some skewed structure or flattened uh, uh, and these kind of things. So pancaking basically means that the theta, the theta will increase. Okay, so when the CME is going forward, there might be some restriction. So that due to that restriction, it can flatten. Okay. Or over expand in the theta direction. So that is basically flattening and pancaking. And skewness you already know. Let's say that this wing, instead of going like this, distorted in some manner. So that will be kind of skewness. So the density and temperature are still being taken as the homogeneous thing because we are not able to estimate it from the chronograph images with a high confidence. So right now we are taking the homogeneous, but the speed, uh, if this movie plays, okay. Okay. So if I allow this flux rope structure, which is formed on the basis of the chronograph images, and if I allow it to expand, so this is the point 1 AU, which is the boundary of our coronal MHD domain. So you can see this is expanding, and this overlapping area is being provided here, and this is basically going inside the MHD domain. Okay. So okay, so this is better rather. So you can see these are the field lines, and we are getting those Bx, By, and Bz components. So it's in Cartesian, we'll transform it into spherical, no problem. So this is how we are incorporating the flux rope inside the MHD domain. So we have an initial structure using chronograph images. We allowed it to self-similarly expand, and as it expanded, it crossed this inner boundary, and whatever value was at the inner boundary is getting inside the MHD domain. Okay. So hence the CME structure will form. Okay. Oh, okay. I'm not showing any video. Maybe at the end I will show a CME nice one video. So let's say that we have simulated it nicely, and now we are comparing with the observation. So leave the cone model. Cone model is for this teal color, and just focus on the blue one, and the orange is the observation. And the shaded region is CME affected area. It has multiple CMEs, rather 5 CMEs in this current rotation. And beyond the shaded region, it's only ambient solar wind. So first just check the ambient solar wind. It is matching this one, it is matching this one. There is some magnitude difference, but the structures are being captured. So the ambient solar wind is nice. Now let's talk about the CME. So these vertical lines are corresponding to the arrival of those CMEs at the spacecraft in the observation, obviously. So you can see this is the arrival of first CME. The velocity rise is not very significant, but you can see in the density has risen pretty much quite enough. So this is first, this is second, and correspondingly 3, 4, 5. For the first one, we can see the flux rope is arriving at this point. Point of okay, because their sheath region is at this point. So by sheath means when the CME is propagating, it is generating a shock. Okay, because you know what is shock? Okay, great. So when the CME is propagating, it will generate a shock, and it will aggregate materials in front of it, and that aggregated material region is called actually sheath. Okay, so the sheath region is rather with that region from where the rise starts happening. So just look at the bottom of those spikes. Okay, so you can see there is some difference. In the second one, there is not much difference, not also in the third one. In fourth one, there is some difference, and there's some difference in the magnitude also in the last one. Okay, that's about the velocity plot. So from these, you can talk about the arrival time estimation of the model. Means at what time, based on the chronograph images, the CME will hit the Earth. Okay, so this accuracy is roughly less than 5 hours. Okay, for this specific CR period, and this is for density, and this is for temperature. So this is basically comparison with the observation, the time series plot, just to validate that the simulation is working finely. Because if you don't validate, then how will you say that your model is working? Okay, so that is very important. So just if I just magnify it, then it will be nicer to see. You can see some difference here. So it will be roughly around this might be like 6 hour thing. Yeah, 5 to 6 hours. These things will be lesser, and again 4 hour, and then maybe 2 hours. So this is the current accuracy of this Swasti CME. So let me show you now some nice plots. Okay. So that's all about validation. Now we have validated the model, and now we have to do some physics kind of things, that what can be done from the model. So this is basically what I'm showing is the CME structure. Okay, this is CME structure, and this is the ambient solar wind. Rather, there is some threshold. That's why everything is not present there. Rather, just only the stream interaction regions. Okay, and this color map is corresponding to the ram pressure of the solar wind. Okay, so you can see if you look at the top, the CME originated from here and it is propagating. And if you look from the front, and this is how the CME is looking. So from this image, you can directly conclude that CME is not a flat thing, okay, or very smooth surface. You can see some distortions has happened, mainly because of the solar wind. You can see this here, the ram pressure of solar wind is very high or maximum in the plot, and some at this location and some at bottom. So just you have to just imagine that if you are underwater and you are moving any object, so what will be the motion of the water due to that object? The same thing is same thing is happening here also. Okay, some things are going up, something down, something right, and something left, and in that interaction, this deformation is happening. Okay, and this deformation will largely depend on the structure of this SIR. So SIRs are not 1D thing. Okay, it's like 3D structure. The 3D solar wind streams are interacting and 3D structure is forming. As you can see here, they have 3D morphology, a 3D structure. And that 3D structure kind of highly decides what will be the deformation of the CME front. So if I just take a slice, okay, take a slice of this image, this 3D image, and make it 2D, the CME is still 3D. Rather look on the TV, the CME is still 3D, but I have taken a slice in the R5 plane. And this is now scale density. By scale density means density into R square, because density falls as R square. So if I just multiply with R square, so it will be like normalizing the density. So you can see these are the SIR structures, okay? Highly scale density surface. And this is CME coming forward. So you can see initially the CME was very smooth and symmetric, but rather as it expands radially, there are some deformations. You can see, but if you look here, the texture is very coarse here. Rather, it's very smooth or relatively smooth at this point. And this SIR is getting kind of destroyed by the CME. It is aggregating more and more material, and you can see the higher density regions are forming at this point. But the CME is still 3D. That's why we are not able to look behind this one. So if I take the slice of the CME also, so now you will be able to see. Rather, I will recommend to watch on the TV. This one is not very looking nice. So now we have plotted the solar wind speed also. So now you can see, but the window is very high. It's 200 to 400, 400 to 600. So whatever the variation is behind this, between this one, that will not be seen in these plots. So you can see there is a fast wind and there is slow. Again, some variation, and stream interaction regions are there. Okay. And the green is for the CME, traced CME structure. So the challenging part is to isolate the CME structure from the solar wind, because it's the same simulation. So we have used something called passive scalar technique, of which I will not talk about much. Just trust me that we have isolated the CME structure from the solar wind. So this is the green one. Now you can see this is line contour. The blacker line means greater density. Okay. So when the CME is evolving, you can see at the nose of the CME, higher density region is there. And additionally, why? Because the SIR is at this point. And as the CME advanced more, the SIR, the position at which it is interacting with SIR is having the highest density. So these kind of conclusions can be made from the simulations, okay, which is giving a 3D picture, the total picture, assuming your model is right. Okay? Because in as we already talked, in heliosphere, it's very difficult to do remote sensing observations of CME. And in situ, we'll only get one data point, okay, like one location thing. We'll not be able to talk about the whole phenomena. The whole complete picture will not be able to conclude about that. So these are some things. Again, you can see that the leading edge of the CME is not smooth, rather it is getting deformed. and these are two SIRs through which it is interacting, and at the interaction point, the density is highest. And plus, if you look carefully, you can see the top flank is kind of over expanded as compared to the bottom flank, because that this high speed streams are having low density and hence low pressure. So if the pressure is low, then the pressure gradient will be higher, and hence this part of the CME will expand much more expand more as compared to the bottom part, where the whole flank is not inside the solar wind, fast wind, but the pressure is lesser as compared to the slow one. That's why there is some over expansion also, under expansion also, deformation also. So these kind of things are going as the CME is evolving in the heliosphere and interacting with the solar wind. So the main part that plays in the heliosphere is the drag force. Okay, the same drag force that applies everywhere in the air. Same thing is here also, which is dependent upon the ambient density and the relative speed between the solar wind and the CME. So if I just draw the map of the drag force acting on the CME front, then this is what I will get. Okay, so initially you can see, okay, the color maps are not visible much, but the red one is for higher values and the purple is for the lower values. Okay, so you can see the drag force is very high at this point and gradually it has decreased. But if you look carefully, you can see that one structure is forming and that structure is going leftward. So this structure is going leftward. You can see this is at this position. Earlier it was rather at this position. So this is corresponding to the first SIR as it was interacting. As you can see this one. Okay. So it was moving forward, it was interacting this point. So this at the nose, whatever the material has aggregated, due to which the drag force due to which is being reflected in these plots. Okay. And this is the histogram showing the surface on which they are acting. And you can see clearly with time, they are overlapping, the negative drag and the positive drag. By negative and positive, I mean the CME is pushing the solar wind and sometimes solar wind is pushing the CME. So that is positive and negative. Okay. So from here, you can say that the negative and positive force area is kind of getting a balanced state. You can see clearly from this, or you can again do some more rigorous analysis, and from there you can make this conclusion that the area of this positive and negative drag are getting a balanced state. Okay, and that might have very interesting results. And to study that, we can do one thing, that once we have formed our model, now we can create different things. Okay, not necessarily realistic things, unrealistic things also. And how that can be useful? Let's say that I have created a real case. Okay, this is a real case where everything is observation based in a default setup that we have already talked about. And there is an ideal case. Okay, now I will do something different. What I will do is that I will assume that speed is constant everywhere almost in the initial condition, due to which what will happen that in the inner heliosphere also, the speed, you can see the variation in these two things. This is the real case, this is the ideal case. So the speed is almost uniform in the inner heliosphere, and this is the scale density. You can see there is no SIR formation because the speed is uniform or constant. So there is no interaction region. So there is no compressed region and hence no enhanced magnetic field, enhanced density. So it's a very simpler case. So it can be called as a very simplistic case or ideal case, and this can be called as the real case. You can see the magnetic field also, there is a complex geometry and a very simple dipole-like structure is there. Okay. So now we can say that there is no SIR present, no high speed, low speed streams are there, and no high density regions are there. So it's kind of more symmetric as compared to real case. So what if I inject a CME, identical CME in those two scenarios at the exact location? So what will happen then? There must be a few things, there will be some differences arriving, and that differences can be claimed to be the effect of solar wind on the CME, or rather the high speed streams, low speed streams, and the stream interaction regions. Okay. So that this kind of studies can be done using the simulation once you have made your model. So what I did is that I have traced the CME, 3D CME. Now I can compute its volume. Okay. So computing volume is also very interesting thing. So this is the plot of the volume of the CME. You can see this is the time By time I means the CME was at 1 AU, and then it started propagating in the MHD domain, and that is the time elapsed. Okay, so this is the point where I injected the CME. You can see it is a kind of rising, and if you take log scale, then you can say it's a power law. Okay, so by power law means volume is proportional to T to the power something. Okay, so in both cases, whether there is a realistic ambient or ideal ambient, it is giving power law. Very interesting thing why we are getting power law in both situations. And if I do a like more rigorous thing, then we can plot this slope, which is T to the power alpha. And if we get a straight line, then you can, with more confidence, you can say that this is a power law. And what is the power of T? That is, in the ideal case, it is more, and in the real case, it is less. You can say 3.25 and 3.03. So these are for two different current notations. 2165 is close to solar maxima, and this is 2238 is close to solar minima. So in both things, CME is giving power law, same kind of thing. And again, the ideal case is expanding more, having more volume as compared to real one, which is kind of obvious because as it is interacting with the solar wind, expansion will be lesser. Okay, so that's all about the volume, I guess. So there are many interesting things that can be drawn from here, but I will just focus on the model, not the results of it. But trust me, there are many things. You can talk about that how the volume is expanding, like whether it's adiabatic expansion or not an adiabatic expansion. What is the role of ambient in the evolution of the CME properties like pressure, temperature, how they're affecting. So these things can be directly concluded from the simulations if your model is right. So now coming to one last interesting thing, that is CME interaction before we end. So there is nothing much, just a video if it plays. So CME interaction is another interesting thing. We can see that there is one CME, second CME, and third CME. The third CME has already did the second one. And there are multiple chains interacting. You can see even the last CME which originated is kind of beyond this point is interacting with that one. Okay. So it has multiple interesting things. One of the most important thing is that how the interaction between these two CMEs are kind of bringing the changes in the front CME, and that change might be more geoeffective. Okay, means it can impact us even more because two heavy things are colliding or energetic things are colliding. So something dangerous can happen or something more energetic thing can arrive from that one. So it is based on the geoeffectiveness, and geoeffectiveness is basically governed by the magnetic field orientation of this one. By this one, I mean the CME or the solar wind plus their momentum, okay, like their density and speed. So these things are also important. So if you just have questions, you can ask. But before that, I will say that you might be having two questions. How to start working with MHD simulation. So I will just say you can go to these open source codes. I personally use Pluto code. It is very versatile and has many options. You can do many things. AMR WAC is also there, which is equally good. All of them are equally good. Athena is there. So AMR WAC is European thing. Athena is US thing. Okay. So you can take some given examples there. Okay. And then you can try to understand what is happening. So there are already made up systems which you can directly run and then can understand what is happening. Then you can plot and do analysis. So once you have developed these things, then you can play around. Okay. So like any other thing, to learn doing this simulation, you'll have to do it. Okay. So you need to play it around, and then you have, if you just want to analyze the simulated data, okay, you don't want to simulate it. You just want to have results. You don't want to make the model. Then what you can do is that there is something called CCMC. This is a community-based platform where most of these models which I talked about, which was INLIL, Space Weather Modeling Framework, those are available here. Not for free, their codes are not there. They are not open source. Rather, we have this something called request a run. So if you go to that website and there are different things. If you choose INLIL and you say that I want to request a run for the solar wind for this time period, they will do their simulation and send you the result. Okay. So from there you can plot and do many things. Okay, they will even plot for you. There are widgets for that. And another thing is that we are also coming with something called run on request portal, which is under development for this Swasti. So anyone can go there, go to that website and request a run for CME or solar wind for that current notation. And most probably we'll also make this Swasti open source, means freely available for everyone, maybe by the end of next year. Okay, so that's all from my side. Thank you.
So when you showed us the observations of CME, there were a lot of plot data with velocity, density, and everything. There were a lot of fluctuations there. Like there was a down and then there was up in the 20s.
It's a very nice question. Yeah. So there are fluctuations then.
So the fluctuations, I wanted to know the reasons for the fluctuations. In the
Okay.
20s, like there are very minute fluctuations. It is going down, it is going up the speed.
Yeah. Let's talk about this one, right?
Yes, sir.
So there are, as you said, fluctuations. So there are many fluctuations like alpha-link fluctuation. Plus, I think this is more. I'm not very sure, but I think this is more related to turbulence. Okay. So if in the realistic environment or in a turbulent medium, so solar wind is a turbulent medium. So you will not have a smooth these lines, rather a fluctuating one. So this is more like these are basically the fluctuation, not interesting things. If you are not studying the fluctuation, so might be rising from the turbulence of the solar wind.
What are the reasons for the turbulence which are
Okay.
not usually thought about? Like we know the magnetic field, the solar wind drag. Are there something else that we can consider in taking into account?
Okay, cadence. No, it is not due to cadence. That's for sure. It is mainly due to this turbulence. But your question is that why this turbulence is
Yes, sir.
arising?
Yes, sir.
Okay, so that is again an interesting question. So why turbulence is arising? So turbulence happens when you know that there is something called Reynolds number.
Yes,
And
sir.
this, so when that medium can be turbulent, okay, there is something called laminar flow and turbulent flow. When there is a suitable condition for the medium to be turbulent, then it will be turbulent. And in turbulence, what happens? It takes the excess energy at the large scale and give it to the lower scales. So that is what turbulence means. There is some extra energy available which is not being transmitted through the existing processes. So it will take that extra energy and impart it to the lower length scales. So that this is what happens in the turbulence. And because we know that the solar wind is turbulent, so those fluctuations are obvious. But I'm not very sure. It might be containing different things also, different fluctuation, but turbulence is surely there.
And sir, the contours you made, they look really good. What did you use to make these contours?
Contours by this one or the earlier one?
So, all most of them.
Okay, the matplotlib, matplotlib.
All were made using Python.
Yeah, all right.
Thank you.
Any more questions? Sir, how did you take in account of the rotating interaction region?
Yeah,
Because only stream interaction region we can see.
so there's a minute difference between stream interaction region and co-rotating interaction region. So stream interaction region is mainly a general thing. Okay, so whenever high speed and slow speed are interacting, it is called SIR. When that SIR structure remains in that form for larger period, mainly at least till one current rotation, that is called CIR. So CIR is a special case of SIR which lasts longer, at least one current rotation. So if I'm talking about SIR, I'm actually talking about CIR also, because SIR is more general.
And sir, can you come to that pancaking? At what exactly causes that? Means what impedance to CME does that?
Okay, for pancaking, I will rather go to this point. Okay. Okay, is it visible in this one? I think. Okay, so see that this CME is going forward, and there are some ambient. Okay, so what can happen if you look at this one? The curve of this flank and the curve of this flank are not same, rather different. This is a skewness. Okay, and if he is going forward, and this the leading edge, the circular arc-like structure, if that radius is getting increased, or rather it's getting flattened, that is called flattening. And the pancaking, I think, is that when it is going up, this thing, rather flattening, this thing will also elongate. So this is called pancaking, right? I think that is pancaking.
How does it differs from expansion? I actually cannot visualize.
It is not occurring due to expansion, rather due to interaction with the ambient. Okay. So imagine if you have something very soft, okay, and you have a similar kind of thing in the ambient, and if you drag it, it will rather become flat, and it will also elongate in this direction, theta direction. So that is what is happening. So this is panking, flattening, and skewness will also happen.
Thank you, sir.
Okay, you have a question.
So mine is like, I think I missed that, but what are the input parameters that your model takes to predict or extrapolate these things?
Okay. So for solar wind, okay, just leave it. For solar wind, we have magnetogram. That's the only observation-based input. If we have the magnetic field at the solar surface, from there we extrapolate, and based on empirical relation WSA and on some like conversion of kinetic energy in these things, we have all those properties. We only need the magnetic field at the solar surface.
I'm
for
sorry,
solar
what was that? You have all the other properties from?
we have speed from WSA,
Uh-huh.
and if we assume conservation of kinetic energy, then we have density,
Okay.
and we have extrapolated the field lines. So we have the knowledge of the field line, or the value of the field lines.
Okay.
And plus, if we take thermal pressure balanced state at this point, we can take constant pressure.
Okay.
And the long term, or from iteration, we can say that value should be close to this point. And for CME, we are using coronagraph images to estimate its kinetic and structural properties.
I was just like, what are the implications of actually predicting CMEs using your model?
Okay. You mean the usage of the model?
Yes, yes.
So the usage is that you can form something called alert system. Let's say if you are talking about the forecasting thing, that if you have model, if we see that the CME has originated, okay. So now we want to know whether it will be geoeffective, whether it will be hitting the earth, when it will be hitting the earth, and through the simulation, what can be deduced about how impactful it is going to be the CME. So these things can be computed, and from there we can generate an alert system. That at this time, so it is very in the futuristic thing, but we can generate alert system where we can just say the power grid system, or we can shut our satellite, or we cannot deploy a satellite at that point. Just the SpaceX things that happened, that can be prevented. So these things can be made. It's just like having a forecasting alert system.
It's just that I don't know if I'm accurate about this, but usually these models are very complex and they take a lot of time to run.
Yeah.
I mean, does that happen within the time period the CME will hit?
Yeah,
off?
it happens. So
Okay.
the results I have shown for CME, it takes around 10 to 12 hours.
Okay.
On my 48 core CPU. If you give more cores, it will be faster, but it will not be in 2 minutes. Okay, it will take hours. The time span will be hours. So it will be like that.
Thank you.
Yeah, so for example, in this particular diagram, what are the individual lines within the flux rope? What are they representing?
Magnetic field lines.
And like they're like random sample points, like Monte Carlo, you are simulating the magnetic
No,
field
it's
like
not
that.
Monte Carlo. Rather, it's based on Lundquist model. Okay, so if you have a flux rope structure, so we have to populate with the field lines or the orientation of the field lines. And there are some different models. The most basic one, or which works quite good, is the Lundquist model. So we have used that one. So what I'm showing here is the magnetic field lines, but with the random in theta direction only. Okay, that's why if you see in the movie, they kind of, some field lines vanishes and some other appears. So because it's random in the theta direction, the seeds are random.
Also, in one of the the observation versus prediction, one of the plots, in the density and the temperature prediction, the model MHD model was very off from the observed. Can you show that plot again?
Okay, yeah, that can happen. No. Yeah, this one. Are you talking about this one?
In the previous one you showed, like,
This
yeah,
one
yeah.
or the earlier
For
one?
example, the temperature and especially the magnetic BR. For example, around 22nd of June, the BR is like very off, like it's almost flat for all the models and the
You're
observation.
talking about this portion,
Yes,
right?
yes.
Yeah. So the main reason for this specific case is that if you observe corresponding to this one, this density region, that is getting underestimated. Okay. So the main rise in the magnetic field, that is Cth region, okay, comes from the compression of the Cth region. So as we are underestimating this density of the Cth region, you can see very like in a very small time, the rise in the density is very sharp. So it's very sharp peak. So that means in that location, the magnetic field also rise very sharply, which is not very well captured here. Then the second reason being that it might be a possible thing, or rather it is, I have checked, is that whatever the flux, magnetic flux we are assumed it to be of the CME, that is actually underestimated. So we don't know the magnetic flux of the CME or the magnitude of the magnetic field inside the CME from observations. So what we do is that we take some standard value, okay, and we assume whatever the CME, let's take that value, because in each run you will not iterate and take out the tune and get the perfect value. So that those two situations are forming this flat-like structures, and plus even if I change this Riemann solver, then even then I will get better result. So there is something called Riemann solver which solves the Navier-Stokes equation, and I have taken HLLC, which is mainly focused on this contact discontinuity. But if we change it to incorporate much betterly the shocks, then we'll have better results at this point. So there are multiple things, and we have to take in account the whole thing, that on average or overall, the result should be better. So in that situation, some of things might go haywire. Okay. So that is one simple example here that you have rightly pointed out.
And is the error in the density and the temperature, can that be rectified by a proper equation of state? Or do you think the equation of state which you are using, the 5/3 and adiabatic and the variations in another plot, is it the only responsible factor for the error, or there can be other source? Why it is off?
Yeah, that can be like some percentage of that thing will also be there, because it's never going to happen that the solar wind or the CME will have some constant gamma. Okay, so it will be varying. So one way to incorporate is to do thermal conduction. If I incorporate thermal conduction, then instead of 10 to 12 hours, it will take 15 to 18 hours. Okay, so it's up to you when you want something, whether you want computationally more accurate, more robust thing, or you want to trade it with time also. Okay, so there are multiple things. There is something called computational power, how many computational cores you have, and how much time you want it to be solved. Okay, so these things has to be balanced. So it's kind of a trade between these two.
One last question: what is the adaptive? What your phrase in the Swasti is used?
Okay.
How is it adaptive?
Okay, so actually it was just to make the Swasti word acronym, but there is a meaning. There is a meaning that we are also planning to involve machine learning algorithms there. So that's why we use the adaptive term there. So which is ongoing work.
So I have a very general question. Actually, your Swasti model sounds pretty interesting. And how was your research experience of getting into a new model like this? And what do you think Swasti is different when compared to other existing MHD models?
So other existing emerging model, I won't say emerging, they are already well established. We are kind of emerging. So starting with the first part, it was not very difficult. I was kind of interested in doing computational thing. So I started doing, and gradually you already have that much literature. So the advantage was that already different models was there. So what I did is that I compared those models, and made systems and figure out which thing is working best in that particular case. So it's kind of we kind of took the best part from each model and incorporated in our model. Okay, so that was the thing that of kind of easier if someone has already done. And the second one was that the difference is basically, that is the difference that in some locations you can see that these values, that the constant pressure is not 6 nanopascal, rather 3.3 nanopascal and something different. And from there we have seen that if we take this value, then this will give better results. So we have iterated many times to see that which one is giving better result, and we have tuned it in that manner. So some part is matching with some other models. So it is like that. And plus, if we talk about the how versatile or robust is the code, so we have large window. If we want to make it more and more computationally accurate and robust, we can go to that one. Or if you want to make it quick, then we can go to shift to that one. So these are things we have large window. Others also have, but as we are using Pluto code, so Pluto code has more things to incorporate. Like I talk about the Riemann solver. In that manner, you have also something called technique which solves this divergence cleaning. The divergence of B should be 0. So that should also be there because it's a strict law which has to be followed. So you have to put a equation or a method that takes care of that. So that different things, so that can be done. So it's more versatile, I would say. And if we compare the results, then I have not done a rigorous comparison, but I have seen that as compared to Enlil, the solar wind magnetic field and speed in most of the cases are giving better results as compared to Enlil. But I cannot comment like this one. We need to do some rigorous analysis plus with their collaboration, because I don't know what's their real code. I only see the CCMC results in other papers.
Okay, if not, let's thank Prateek.
Thank you.
So now we break for tea, and then we have to come back 11:35 or so. We can come back. Okay, we have the next talk online, so please be prepared.